Okay, so welcome to like session two, and yeah, uh, yeah, we can start. Let's see if any others can join or not. So, how will we proceed today? How will we proceed today is like same means we'll have some MCQ type questions, we'll have some numericals, and we'll try to cover whatever has been covered in the earlier lecture videos, right? So by doing that, what we will cover is as follows. So we will cover uh, different types of weld joints. So typical weld joints you are aware of. What are different types of joints? Then we will briefly cover welding microstructure. So that will be very brief, not in much detail, to get some idea. And then maybe we will move forward to some gas welding basics. And after that,
I cannot hear you.
is it is it better now? Can you hear me?
Sir, I cannot hear you.
Now, am I audible? Hello? Yeah, Pranjal, am I audible? Can you please confirm I'm audible or not? Audible. Okay. So as I was saying, we'll have some gas welding basics, and then we will move to this physics of arc initiation. How does arc occur, and those aspects. So we'll move to arc physics, and then some fundamentals on shielded metal arc welding, gas tungsten arc welding, those different processes, right? So we go to shielded metal arc. So these are our coverings of today's session. Now let us talk something on these types of weld joints, right? So in terms of types of weld joints, in terms of type of weld joints, what are different types of joints you are aware of? So mainly if you see, there are four different types of weld joints. So there is something called, uh, let me write it down in this way. What are this? We have something called bead weld. We have something called groove weld, then you have fillet weld. You also can have something called plug weld, right? Now, bead welds are also called surface welds. So they are made directly onto a flat surface, right? So how does they look like? So this is if I try to draw some 3D image, they will look something like this. Something like this, right? This is my weld bit. So this is how it looks like in surface weld. In so basically this is happening on a flat surface, so therefore it does not require any edge preparation, right? Now over here the penetration depth is really limited for the melting. The penetration depth is limited, and when they are used, bead welds, they are primarily used for joining thin sheets. So bead welds are used for joining primarily thin sheets. So if you want to building up some surfaces or some cladding kind of thing, or some depositing some, let's say, wear resistant materials, doing some coating kind of thing, on those aspects mainly those surface welds are used. When does groove welds are used? So groove welds are used when you want some you want some full thickness strength of the material, right? You are doing some thick material joining, and uh, on those aspects groove welds are used where you need some kind of edge preparation. So there can be different kinds of edge preparation. You can have some V, double V, U groove, J groove. So these are different kinds of common grooves which you can prepare to make a groove weld. So how do they look like in groove weld? So if I draw the cross section only, they look something like this. So you want to make some kind of groove, you know? So it will something like this, making use of the complete thickness of the material. And they can often be produced by some process called oxyacetylene flame cutting. These groups are prepared, can be prepared with oxyacetylene flame cutting. So as I was mentioning, there can be specific types of grooves, and those grooves which you want to prepare, that depend on thickness of the joint. That depend on what welding process you want to employ, right? Okay, and then you can have fillet welds. So I talked about bead weld, I talked about groove weld. You can have fillet welds also. When do you want to use fillet welds? Fillet welds can be used for some configuration like T joint or lap joint or corner joints, right? And they also do not require any special edge preparation. And yeah, they also do not require any special edge preparation. And then you have this plug weld. So in plug weld, basically you will attach one part on top of another, and they often used. Sorry, I lost my connection. Is the screen visible now?
Yes, sir.
It has some poor connection. Yeah, okay, thanks. So I was talking about this plug weld. Uh, Plug weld, basically you are attaching one part on top of another, and they're often used to replace a rivet or bolts. On those aspects, you can use plug weld, right? Now, in terms of joint configuration, what joint configuration you can think of? So you are aware of this configuration, right? So let me write down joint configurations. So you are aware of, let me drop this off. You are aware of butt joint. Let me not go into the detail of how does they look like. This is well aware of. You are aware of left joint. Then you can have something called T joint. Then you can have corner joint, something called edge joint. So these are different kinds of joint configurations, and that can be made with use of either bead or groove or fillet welds, right? Now, now, in selecting the type of joint to be used, so what should be the primary consideration? The primary consideration should be the type of loading which you want to apply over that weld joint, right? So basically, it depends on what kind of failures is happening. Yeah. uh, Is there any problem? Okay. So, hmm. Now let me draw something in terms of different weld procedures which are used to produce these weld joints. So can you tell me what is this joint will be called? Let me draw first and then try to tell me what can be this kind of joint, right? So what is this called and what is this called? Anyone?
Butt joints.
So of course this is butt joint. And by looking at the configuration, what can you tell?
Single butt joint, double butt joint.
One is single V group, another is
Double butt
double V group, right? So there are some consideration of why you should use single V group, why you should use double V group. I'm not going into on that direction. Anyhow, so by looking at those configuration, you can identify what kind of joint configuration is this, right? Okay, so we have briefly talked about type of weld joints. Let us talk something on weld microstructure, right? So now we will talk about weld microstructure. Let me first discuss a bit, and then we will move to questions, right? Just like the previous day. So we'll talk about weld microstructure. Now, why does there will be change in your microstructure in welding? Because you are doing some kind of heating and then you are doing some subsequent cooling of the weld, right? So there will be different regions in your weld microstructures. What can be those regions? So what are different regions of weld microstructures? You have fusion region, you have fusion zone, you have what is has.
heat affected zone.
So this is called heat affected zone. Now, if you are doing any solid state welding process or you are doing some kind of deformation based joining process where you are applying pressure along with heat generation, you are also deforming the material. Then there is something called thermomechanically affected zone, TMSF, right? So we'll call it thermomechanically affected zone. And then you have your base metal or original part, right? Okay. Now, as I was saying, those metallurgical changes, those significantly affect the quality of weld, obviously. Now, what are various factors? What are various factors for which these changes are taking place? So you can have the nature of material. So in terms of nature of material, either it can be single phase, it can be two phase material. Maybe you are mixing two metals, dissimilar metal joining. So it depends on the nature of material. It can depend on your any prior heat treatment if you are doing, or any preheating kind of thing if you are doing. That also can change your microstructure. So that is another aspect. And what else can affect your world microstructure if you're doing any deformation based process, or we'll call it prior cold working, right? Let me get this up. Okay, so let us consider first the fusion welding of two pieces of single phase material, right? So, and we'll assume that this has been cold work to get some desired grain orientation. Okay, I hope these things are you are aware of those terms: grains, grain orientation, single phase, multi-phase materials. And what happens due to cold working? So cold work grains will result in high strength and low ductility, right? So if you are deforming a material, there will be dislocation generation, right? Are you aware of these terms? Just the terms in metallurgy. Yes or no? I need some response, please.
Yes, sir.
Yeah, great. Then you will be comfortable. That will be good for me also. So if you are doing cold working, you'll have some desired grain orientation, and that will result in a high strength and low ductility, right? However, when you are melting a material in fusion welding, uh, there can be random grain growth which will take place within the melt boundary, right? Let me draw something. I will try to draw it. So I was talking about the single phase material. How will it look like? Yes. So this is my melt boundary. Okay. This is my heat affected zone. This is some region adjacent to the heat affected region. And over here, this is base metal, green. So over here you will see some elongated kind of grains, right? In casting also you have seen, due to temperature gradient, uh, from the surface to the center, there will be some preferential direction of solidification, right? And because of that, grains will be much more elongated. And then over here you will have some coarse grain structures, and comparing to that, you will have some fine grain structures towards the base metal regions, and then you will have uh, these rolling kind of thing. So initially it was all rolled sheet, right? It was all rolled sheet. It will be unchanged over base metal. So that is in rough. It will look like something like this, and yeah. So I was talking about during fusion, there will be some random grain growth which will takes place during within that male boundary, and that will in turn also result in a low strength over here. That will also in turn in a low strength. Now within the heat affected region, the grains become coarse due to some, that if you are doing some annealing kind of thing, you are doing some heat treatment, there will be some coarsening of the grains, right? And there will be also some partial recrystallization that will also occur. And in either of those cases, the strength will fall much below of the parent metal. So if we try to understand in terms of a graph, how will it look like? So it will look something like this. It will look something like this. So over here, this is my base metal. So my strength will go down. My ductility will come like this. This is strength. This is ductility. Right? Now, if you consider some two-phase material, right? This I was talking about single-phase material. So you're joining aluminum to aluminum, you're joining copper to copper, steel to steel. If you are joining dissimilar metals or two-phase material, what is the most significant factor that will derive its strength? There will be something called precipitation formation. So I will call it, that there is different hardening mechanism. So we call it precipitation hardening or edge hardening, which will govern the strength of the joint if you are doing some dissimilar metal joint, right? And over here also the strength within the male boundary will be too low, but in the immediate adjacent to the heat affected region, the thermal cycle, basically you are doing heating and then quenching, and if you are doing some age treatment, that aging process will recover some strength in that weld region. The material beyond this region is only overaged. So if you are thinking of this region, this is overaged, and adjacent to this heat affected region, this is aged. So how the strength and ductility will look like in, if we try to understand in terms of a graph. So my strength is this, and it will increase a little bit due to this age hardening mechanism. So this is strength, this is strength. And what will happen to ductility then? My ductility will look something like this. Over here, this is my base vector, right? Okay. So this is very brief on weld microstructures. There are huge amount of uh, things are there in weld microstructure. This is itself a different subject at all. Till now, any question?
No, sir.
Mm-hmm. So we have talked about type of weld joints. We have a little bit talked about weld microstructures.
So I have a doubt.
Yeah,
The figure in which you show heat affected zone.
I'm not
But
getting.
so
Can you come again?
the figure in which you uh, tell about us. Yes, sir. This figure. This the structural types are name. Please repeat.
I can't really hear you. Can you message? Can you just type your question in the chat box? I'll see, and if I will try to
Sir, the structure names.
the name,
The names of structure in
the name
different
of
zones.
structures. Yes.
Yes, sir.
Huh. What happened to the name of structures?
Uh, please repeat it.
So I was talking about this fusion region, heat affected region,
Yes,
thermomic.
sir.
Acha, I just rubbed this up. You want those names of the structures again?
Yes, sir.
Okay, sorry. So let me write down over here.
Yes,
So you'll have fusion region, have heat affected. You will have, so this is specific to solid state process, because in normal fusion welding, you are not doing any kind of deformation, right? So if you're doing some ultrasonic welding or friction stir or something like that, then uh, pressure will come into picture. So thermomechanically affected, and you have base metal or the unaffected part. Okay. Okay. So next we'll move to gas welding, a little bit on gas welding, different kinds of flames, what should be the ratio, what gases should be used, those aspects, and then maybe we will try to figure out, we will try to figure out questions from whatever have been covered. So I can see in the questions, one question is there from the gas welding. this one. So let me first go through the gas welding part, and then we will discuss on discuss question number one. Okay. Now, in terms of gas welding, as you know, this is also called oxyacetylene flame welding, and basically you're joining metals by heating with a flame that will the flame will be a result of reaction between fuel gas and oxygen, right? Oxygen and acetylene. Those are most commonly used gases which will result in a flame which will produce high flame temperature that will result in melting of your metal, right? Now, you can use some kind of flux that can be used uh, to deoxidize or clean your weld metal, right? So during that point of time, the flux also will melt and solidify and form some kind of slag slag formation, right? On your resultant weld metal. Now, what are different kinds of flames you're aware of in gas welding? Can I rub this off if you have taken the notes? Anyway, will I am taking this off. Okay. So, what are different gas welding flames? Hmm?
Carbonizing flame, oxidizing flame, and neutral flame.
Great. So you have neutral flame. You will have neutral flame. So here oxygen and acetylene are mixed in equal amounts, right? And uh, they will be burned at the tip of the welding torch. So how we will characterize a flame. So over here, if this is your torch, let me first draw and then I'm explaining. So this is also called carbonizing flame, also called reducing flame. Hmm. So how will you characterize a neutral flame? As you know, you are mixing oxygen and acetylene in 1:1 ratio. Here in a neutral flame, it can be characterized with a short inner core and a longer outer envelope. So in neutral flame, you will have this is called inner core and this is called outer envelope. So neutral flame can be characterized with a short inner core and a longer outer envelope, right? So inner core is the area where some primary combustion is taking place through the chemical reaction between oxygen and acetylene, right? So yeah, heat of this reaction that will be accounted for about two-thirds of the total heat that will be generated into that inner core. Now, what are the products of primary combustion? So um, if you are mixing oxygen with acetylene, what will be the product of primary combustion? So initially it will form carbon monoxide, right, and nitrogen, and then again it will react with oxygen from the surrounding air. So again, CO will react with surrounding air, that will form CO2 and moisture, right? So this is called secondary combustion. This is called secondary combustion, and over here C2H2 plus O2. This is called primary combustion, right? Got it? So
Yes.
yeah. So the area where the secondary combustion takes place is called outer envelope. So that is the main funda on what is happening on your inner core, what is happening on your outer envelope. Primary combustion takes place in your inner cores, and secondary combustion is taking place in your outer envelope. Now, in reducing flame, when you are using excess acetylene, right? So that resulting flame will be called as reducing flame. Over here, the combustion of acetylene is incomplete, right? Because oxygen amount is lower. So what will happen? You can basically differentiate the flames with different colors also. Have you ever seen the gas welding flames in your laboratories? If you see over there, uh, the reducing flame also you can differentiate with the sounds also. Now, if you see the colors, it will be some kind of greenish color. Those reducing flame, right? And that will form in between inner core and outer envelope. This greenish color. That will form in between that inner core and outer envelope. And when do you want this reducing flame in picture? If you want to join some materials like aluminium, because aluminium oxidizes very easily, you want to join it with reducing flame with less amount of oxygen. This is also good for welding high carbon steel, right? Because excess oxygen can oxidize carbon and form CO gas porosity in the weld metal, right? So those are the application when you want to use reducing flame. Now, during oxidizing flame, what is happening in oxidizing flame? You are using excess oxygen, right? As simple as that. Now, over here, the flame becomes oxidizing because of presence of unconsumed oxygen. So, how can you characterize oxidizing flame? So, you'll have short white inner core. So, this is very short in nature, and also this will be sharp. If you observe the flames, this is short, mm, sharp. Over here, the sound will be very quiet. Sound is quiet. Over here, it will have some hissing kind of sound. You can differentiate between that you have formed some carburizing flame, you have formed some oxidizing flame. Now, when will you prefer oxidizing flame? Uh, if you want to weld, let's say, brass material, if you using brass material, uh, because copper oxide covers the weld pool and it will prevent zinc from evaporating the weld pool. So that is some idea of why you want to use oxidizing flame as a flame when you want to joining brass material. So what is brass? It is copper plus zinc, right? So if you are forming copper oxide, it will basically covering the weld pool using making a slag over that weld metal, and that is basically preventing the zinc from evaporating and forming the porosities in the world core. So during that task, sorry, I will be using oxidizing flame. Okay, then let's move to question 1. Can you quickly give me the answer of question 1? This is very simple. What is written? It says temperature of a carburizing flame in oxygen gas welding is higher than the neutral flame. Okay. So in terms of temperature, the generated heat that will form during this oxidizing and carburizing and reducing flame. Oxidizing flame will have the highest temperature because of presence of oxygen, and the inner core will be the one where primary combustion is taking place, as I was saying, and then you have neutral, then reducing. So it says temperature of a carburizing flame in oxidation gas welding is higher than that of neutral flame. This is false. So one is incorrect. There is one option where one is incorrect. Anyhow, 4 says oxidizing flame contains. This is again false. My second statement says welding of iron and steel using carburizing flame. Yes, this is true. This is also true. Agreed?
Yes, sir.
Correct. Okay. So we have talked about gas welding part, and then we will try to understand something called emission or ionization of electric arc. So this is the mechanism by which arc will be initiated, right? If you are doing some arc welding operation. So I will call it emission. Yeah. Okay. So let me just draw some schematic. This is my electrode. This is my arc. This is electrode. This is workpiece. Uh, I don't know. Let's say this is positive and this is negative. I will be coming to that. This DC PDC in part, and this is my power source. Right? This is a simple schematic of the circuit diagram of what is happening in your welding. Right? So over here, I have used my workpiece as positive electrode, right? And this is also called anode. These are some known things. This is also called cathode, correct? So what need to be done initially to get the arc initiated. So initially a good contact is made between the electrode and workpiece, and thereafter the electrode is withdrawn. This is a very simple process. So what is happening as a result, when you are touching the electrode with the workpiece, there will be some metallic bridge that will occur to, within that contact region, and whenever you are uh, retracting the electrode or whenever you are withdrawing the electrode, those metallic bridges start breaking. Whenever those metallic bridges start breaking, they will increase the current density. So my current density will start to increase, right? And finally, the current density rises to such a high value, those metallic bridges will start boiling. Okay. And under such conditions, the electrons will come out of both the surfaces, both cathode and anode, by a process which is known as, right? This term is known. This is called thermoionic emission, right? Obviously, the electrons, um, those are having the negative charges that come out of anode, are pulled back, whereas those coming out of cathode are also attracted towards anode, right? So if you are having negative, they are emitting electrons, and they are attracted towards cathode, right? Now there are some analytical formula uh, through which you can estimate the rate at which those electrons are getting emitted from a hot surface. I'm not going into that aspect. There is something called thermionic work function. Uh, then there is something called ionization potential. Those aspects are there, and yeah, yeah. So uh, you just need to understand that if let's say phi is called harmonic work function. You just remember that there is no need to get into the analytical formula as such, but remember that a low value of phi, that makes the emission of electrons easier. So if you are having a low thermionic emission or low thermionic work function, that will makes my coming out of electrons will be easier, right? So emission of electrons will be easier. This you remember. There are typical values of different metals which have been found out from different experiments with time, with years. So those are known values of ionization potential or thermoionic emission work functions. So if you see in terms of emission of electrons, aluminum is much easier. So this is having the lowest value. Then you will have copper. Then you can have iron. Then you can have tungsten. So there are some typical values for these thermionic work functions. Okay, leave it. So next, what is happening basically? So once started this thermionic emission, once started, uh, the arc itself becomes a source of ions, right? The arc itself becomes a source of ions through a process called ionization. So first you are having thermionic emission. Then you are having ionization process, right? So basically over here, the ions are attracted by the cathode and the uh, collisions are happening again and again. So those resulting collisions will keep your cathode hot, right? And you can differentiate. Uh, there can be differentiation of these generated electrons. There are two sets of electrons. The first set emitted by the cathode is called primary electrons. So electrons emitted by cathode, what it is called? It is called primary electrons. And the second set, which is known as secondary electrons, that is a production or result of the ionization of the arc gap. So ionization process results in secondary electrons. Okay. Any question till now? Okay. Now can you tell me, let me knock this off. Can you tell me, let's say you are having an electron of charge E. So this is my electron charge. I'm little bit diverting from the actual discussion, but anyhow, okay, let me finish this. Uh, so my electron is having a charge E, and you are having a electric field of gradient E. So this is my potential. This is called potential, right? Potential difference, volt per distance. Okay. So what will be the force that will be exerted by that electron? What will be the atomic force? My atomic force will be E into E. In other words, it accelerates at a rate of E divided by m. So m is my atomic mass, right? So if it travels through a distance d before colliding with another particle, what will be the kinetic energy? My kinetic energy will be E into d. So this is my distance traveled by that electron, right? So this kinetic energy is nothing but the heat that manifests itself through increased temperature. Because of that kinetic energy, your heat is getting generated, right? So this is in terms of the arc physics. Now, in your arc structure or in your arc characteristics, there are different regions in your arc. So regions in the sense, uh, if you see the potential differences in your arc regions. So let's say this is potential and this is my cathode. This is my anode. You will have some region called you will have some region called anode space. You will have some region called arc column, and finally you'll have the region called cathode space. And apart from those, a small region will be called as cathode or anode spot, right? So the spots are relatively very small area on that cathode or anode surface, which will be either emitting the electrons or attracting the electrons. Now, cathode space, this is a gaseous region adjacent to the cathode spot, and this will also be of smaller thickness compared to your arc column, right? Now, over here in the cathode space, we will have the positive space charge, right? This is easy to understand. And here, the voltage drop that is necessary because electrons are basically to be pulled across this region, you know. So over here, voltage drop is necessary. So in your cathode or anode space, voltage drop is sharp, which is not the case for your arc column region, right? Till now, any question? Let me take some water.
No, sir.
Why don't we why don't we why don't we solve one numerical? Let us solve some numerical. We have talked a lot in terms of theory. Let us try to figure out some numerical. Now, let me rub this up. Hmm, Okay. So in question 2, I have read I have written during a TIG welding process, the arc current and arc voltage that is mentioned as 50 ampere and 60 volt. So my current is 50 ampere, voltage is 60 volt. Okay. Now this is when the welding speed was 150 mm per minute. So V is 150 mm per minute. In another process, the TIG welding is carried out at a welding speed of 120 mm per minute. So let's say this is V1 and my V2 is 120 mm per minute at the same arc welding voltage. So V1 and V2 remains same. Okay. Now it simply asks me if the heat input per unit length, if the heat input per unit length to the material remains same, so that weld quality remains same, I need to determine the welding current for this process, right? So to solve this question, you just need to have some understanding on what is heat input per unit length. So what is heat input per unit length? So if my heat input is Q, what is the unit of Q? So in an arc welding process, you have voltage, you have current. So this is in watt, right? So my Q would be in terms of joule per second. Now if I want to get the idea of what is my heat input per unit length, how can I get my heat input per unit length? This can be defined by dividing your heat input by welding speed. So if this is in joule per second, this is in, let's say, mm per second, I will be getting heat input per unit length in joule per mm. Is it not? So if my heat input per unit length is Q by V, welding speed, and it says that my heat input per unit length remains same for two different processes, right? So Q1 by V1 equal to Q2 by V2. Q1 is voltage into current, right? Now can you tell me what will be I2 over here? It simply says V2 equal to V1. You know the values of velocity 1 and velocity 2. What will be the I2 current for the second process? Just give me a quick answer.
Sir, is 40 ampere.
How much?
40 ampere.
50. So I'm assuming your calculation is correct. Got the idea, right? So if I have got the idea, we will move to, let's say, next numerical. So this question is over. This question is over. We will move to next numerical. Now to solve this numerical, I want to talk a little bit on your power source characteristic. How does it look like? How a voltage current power source characteristic looks like. So let me again rub this out. So it is experimentally found for a given spacing. So I was talking about cathode spacing, anode spacing, right? So it is experimentally found for a given spacing. The voltage reduces up to a current. So it looks something like this. So if this is my current and This is my voltage. It looks something like this. So your voltage will initially drops down and then again it will start to increase with increase in current. So over this region, the resistance will be very low, the arc resistance. And over here, the resistance is high. There are some reasons of why you are observing this kind of phenomena in terms of voltage current characteristic. Uh, let's not go into that direction. Uh, yeah, yeah. Now, because we have some restricted amount of time, I cannot explain everything, but yes. So this will look something like this. Now, as a first approximation, we can assume that if your arc length is L, if your arc length is L, your voltage will vary linearly. So my V will be some constant plus some coefficient into L. So it will vary linearly with your arc length. So over here, A is called electrode drop and BL represent the column drop, the potential gap between your arc column, right? That's how you can characterize or you can relate your voltage with your arc length. Now, this is the voltage current characteristic. Let me draw. This is one, and for some different arc length, this is another one. So let's say this is for arc length L. This is for arc length L plus delta L. Now there are two different kinds of power source characteristic, right? So this is my arc characteristic with voltage current relation, and this voltage current relation will determine the required characteristic of a power source. What are those required characteristics? I need to draw a little bit. This is a little bit tricky. Let me draw it in this way. One is this, another is this. So one is called this is called sharp drooping characteristic of the power source, and this is called flat characteristic of the power source. So what are the operating points of those power source? So this is one of the operating points. This is one of the operating points. This is one of the operating points. So if I am taking this one and this is one of the operating points, right? So there are four operating points by this intersection of the curve. You know? Now this A and B are called stable operating points. Whatever is in this region after this reduction, whatever is happening, that is my stable part. Over there, the arc stability will be higher. Again, there are some reason why there is arc stability, right? Uh, basically, this can be verified by considering a change in, say, let's say you are changing or increasing your arc current. Okay, so over this region, if you are increasing your arc current, So the points shown by this A and B, if there is an increase in your arc current, there will be increase in your voltage. So let's say for operating point A, if you are increasing your current towards this, voltage also is getting increased, right? And this will in turn decrease the source current. So if there is an increase in your voltage, that will in turn decrease my source current. Thus, any kind of disturbance, if it is happening due to the change in arc length or arc gap, because you are doing some manual welding operation, it is very difficult to maintain your arc gap throughout the region. It will definitely happen that your arc length is getting changed because you are operating it manually, so there will be disturbance, right, in your voltage current characteristics. So any kind of disturbance can be automatically opposed, right, and operating points will return to their original values, which is not the case for this region. So that's why this is called unstable operating region. This is called stable operating points, right? So as I was saying, you cannot avoid this change in arc length. That is inevitable, right? Now, that should not cause a large change in your welding current, you know. So this makes the sharply drooping characteristics desirable. So whenever this is very messed up, uh, so the sharp drooping characteristics is desirable in that sense. Okay, I'm not going into detail. Let us leave it over here. Now, let us do this numerical question 4. So in question 4, I tell that my voltage, the relation between arc length and my voltage is 20 plus 40 into L. I just talked about this voltage and arc length relation. And then I say that power source characteristic is approximated by this equation. There is some analytical formula through which you can characterize your power source, V by OCB plus I by SCC into 1. Can you tell me what is OCV and SCC? Any idea? OCV is called open circuit voltage. Okay. So whenever there will be no load or no resistance is attached to your system, or you are not connected your circuit to your workpiece, it is open. During that time, whatever is the potential difference, that will be called open circuit voltage, and that should be high than your operating voltage. OCV of your power source always should be higher than your operating voltage, and SCC is short circuit current. So you're assuming your resistance is 0. Okay. So I have two equations, 1 and 2. What I need to determine is, this is a little bit lengthy numerical. So I will just explain the process, and then maybe if you get time, you can go through that and give me the answer. So there are two equations. There are two equations, V and this characterization of V and I. I need to determine the optimum arc length and corresponding arc power, right? So from these two equations, can I relate current with arc length? Yes. So if my V is 20 plus 40 L and one equation is this, so I can write down 20 plus 40 L is equal to uh, 80 minus 80 by 1000 into I. Have just uh, taken that left hand side to the right hand and then equate the two voltages. And from here I can write down I as 20 80 60 minus 40 L, that into 1000 by 80. Just stay with me and tell me if you are not getting the calculation. Okay. So if I is this, what is power? Power is V into I. You know? So my V is 20 plus 40 L. So I am somehow need some relation with arc length and the power, because you need to determine the optimum arc length and corresponding arc power. So P is 20 plus 40 L into 60 minus 40 L into 1000 by 80, right? This will give me some quadratic equation of L with power. Now to determine the optimum arc length, what I need to do? I need to differentiate with L and then equate it to 0. So to obtain optimum arc length, dpdl should be 0. If possible, in 5 minutes, can you just tell me, if possible, I'm giving you 5 minutes, what should be my L value after differentiation? So you know the P with L relation, and if you differentiate single differentiation dpdl equal to 0, what should be my L value? Is the concept clear? Yes, no. I had my calculations. So you do your calculation by yourselves. and check if it is coming as 0.5 centimeter or not. So I have mentioned where L is the length of arc in centimeter. So L is coming as half centimeter basically, and my P max. So if you put your L value in this equation, you will get P max as 20 kilovolt ampere. Do your own calculations and check if it is coming or not. If it is not coming, then let me know. So question 4 is done. Okay. Now then there is some questions on the polarities. Should I move? Yes, no. Okay. So as you know, there are two different polarities in general is used in gas tungsten arc welding. What are those? One is DCEN, another is DCP, right? One is direct current electrode negative. It is also called straight polarity, or this is the most common polarity in gas tungsten arc welding. This is called straight polarity, and the other one is called reverse polarity, right? Now in straight polarity, your electrode is connected to the negative terminal of the power supply, right? If your DCEN is there, this is connected to negative, this is connected to positive, right? So electrons are emitted from the, if it is gas tungsten arc welding, electrons are emitted from the tungsten electrode, right? And accelerated while traveling through the arc, as I was saying in your arc physics, right? So basically significant amount of energy that is called work function, or I was calling it as thermoionic work function, that is always required for an electron to be emitted from the electrode, right? So whenever your electron enters the workpiece, an amount of energy equivalent to the work function that is released, or I was explaining the kinetic energy of the atom, that will be generated into the heat, right? And this is why in gas tungsten arc welding with DC electrode negative, two-thirds of the heat is located at the work end of the arc, and less heat is generated at the electrode end. So for straight polarity, two-thirds at workpiece, one-third at electrode. The reverse is true for reverse polarity, right? So why this is called as reverse polarity? Because heating effect of the electrons is now at the tungsten electrode rather than at your workpiece. So what is the effect of uh, reversing your polarity? So if you are reversing your polarity, or uh, what we call DC electrode positive, there will be some shallow weld will be produced. Okay? So for DC electrode positive, shallow weld will be produced. And this is the same reason why DCP is used for some welding of thin sheets of some strong oxide forming materials such as aluminium, you have magnesium, but deep penetration is not required. If you need to use some deep penetration or doing some steel material joining, you have to use that straight polarity thing. Now, in terms of electrode, those tungsten electrodes, they are coated basically. They are coated with some cerium or thorium to have some better, uh, what should I say, to have some better electron emissivity, right? To have some better carrying capacity, right? And to get some resistance to contamination than what pure tungsten electrode can provide, right? And as a result, the starting of the arc will be easier. The arc will be more stable if you are mixing those cerium or thorium with tungsten electrode. You know? So electron emissivity refers to the ability of your electrode tip with to emit electrons. I was saying that, right? So let's go to this question. Which of the following is true? It says DCEP results in high material deposition. It says DCEP results in high material deposition. If electrode is positive and workpiece is negative, more heat will be generated at the electrode. So, yes, it will be consuming more, the material deposition will be more. This is true. DCN is results in, tell me if you have some, if you're not agreed with the answers. DCEN results in high heat generation at the workpiece. This is also true. As I was saying, two-thirds of the heat will be generated if workpiece is positive. So more heat will be generated at the anode side. And then I say DCEP results in poor arc stability. So if it is DCEP, that means um, electrode is positive, right? So better arc stability will always be there if it is straight polarity. So electrons, if electrode is negative, that will be the main source of primary electrons to for emission of the electrons and for those uh, generating ionization columns and those things. So DCEP results in poor arc stability. That is also true. So all of these are correct. Yeah. Now to my next question, direct current straight polarity that is used to join thick sheets and used for non-consumable electrodes. So A1 will be matched to B3 and B4 and A2 will be matched to B1 and B2. I had explained this. So this is the next numerical. You have any question?
So please give the reason for the following options in the question number three.
question number 3. Just
Yes,
wait.
sir.
Yeah. For question number 3, I can't hear you.
Yes, sir. I want a reason.
Can you please come again?
Sir, I want to know the reason why the options are correct.
Yeah. As I was saying, this DC electrode positive. DC electrode positive means you're having reverse polarity, right? So if it is reverse polarity, that means my electrode is connected to positive, workpiece is connected to negative end. So as I was saying, the electrons will be emitted from the negative end and it will be attracted by the anode, right? So there will be kinetic energy of those electrons. They will be colliding with some velocity, and that kinetic energy will be transferred into heat. So whenever you will connect or whatever you will connect to a positive terminal, which is called as anode, most of the heat will be generated at that side, right? So as I was saying, two-thirds of the heat will be generated at anode side or the positive side, and the rest will be generated at the negative side. So if more heat is getting generated at electrode side, that will be consuming more, that will be melting more. If it is melting more, it will result in high material deposition, right? Same for the this electrode negative. Whatever I am explaining, the explanation is same for all 3 points.
Okay, sir.
And over here, yeah, you got it right. Yes, no.
Sir, my doubt.
Should I move? Is there any network problem? Can you hear me?
No, sir, there is no problem.
There is some lag, right? There could be some network problem. Okay. Uh, Let me take this question. In this question, I have asked that in our in our welding process, I have measured somehow the arc length as 0.5 meter. This is a cylindrical arc. So my cylindrical arc having diameter of 30 mm, and then I'm telling resistivity of the electrode metal is 2.8 into 10 to the power minus 8 ohm meter. 2.8 into 10 to the minus 8 ohm meter. What next? If the voltage follows a linear relationship, so voltage is equal to 20 plus 40L. I have used the same relation of what I had used in my earlier problem. So this is what it follows. I need to calculate the current drawn from the power supply. This is actually simple. So if this is the resistivity of the electrode, you can estimate the resistance of the electrode material, right? So if this is your electrode, this is your arc. So over here, my arc is cylindrical in nature. So I will draw it as a cylinder. So this is my arc. This is my workpiece. So I know arc length. I know diameter. So you can find out cross-sectional area of cylinder, right? Through which your current is getting passed. So what is resistance then? Rho into L by A, correct? So my resistivity is 2.8 into 10 to the power minus 8 ohm meter. This is 0.5 length and D is 30 mm. So how much meter is this? Huh? This is 0.03 meter. And if this is D, so my cross-sectional area will be pi into pi d square by 4. This will be in ohm, right? I have not done this numerical for myself, but this will give you some value. I don't know how much ohm. Can you give me some quick answer by calculating this? Let's say this is A ohm and getting some finite value of resistance. Then you just formulate it through Ohm's law. So V equal to IR, resistance you have estimated, and voltage follows a linear relationship of 20 plus 40L. So arc length is given as 0.5 meter. So V is 20 plus 40 into 0.5, right? And that is 40 volt. So V is estimated as 40 volt. I need to be calculated. The resistance you can estimate from rho into L by A calculation. So this I had used as A. So I will be some 40 by A into M. Here A will be some finite value. Just get the idea. Any confusion? Okay, we'll move to next question. So I had already talked about this coating with tungsten electrode with cerium thorium, right? It will increase your current carrying capacity. Yes. It will improve the stability of welding arc. Yes. And also it will increase the life of the electrode that I had not mentioned. It will also increase your life of the electrode because your arc is getting stable. Arc stability is higher. Automatically the electrode life will be higher over here. So over here also D is correct. Mhm. In comparison to helium, argon gas in gas tungsten arc welding process falls. There are some options. Now, in gas tungsten arc welding, both argon and helium can be used. However, Ionization potential. There are some difference in ionization potential for argon and helium. Right? So if you see argon gas, it has some ionization potential around 15 electron volt. If it is helium, ionization potential is around 24, 25 electron volt. So which one is easier to ionize, argon or helium?
Organ,
Sorry,
organ.
argon, right? Ionization potential is lower for argon compared to helium. So it is easier to ionize argon than helium. Arc initiation is easier over there. Voltage drop across the arc will be lower with argon. Stability will be higher with argon. Stability will be higher with argon. And also, since argon is heavier than helium in terms of atomic mass, it also offers more effective shielding, right? And yeah, this will offer more effective shielding than helium. So, which one is the right answer? So, I'm just noting it down. So, it will have greater arc stability. It will have shallow penetration. The reverse is true for helium. This is poor. This is deep. Okay. Uh, we have two very short questions. Which of the following is true? Forward and in terms of forward welding and backward welding. As you know, that in forward welding, if this is electrode, if this is workpiece, if this is my welding direction, this is my weld bead metal, this will result in some kind of preheating of the weld to be deposited, right? Over this region, there will be preheating of the material. As there will be preheating of the materials can be melted quickly. So you can attain higher welding speed when you are doing forward welding. In comparison to that, when you are doing backward welding, this is your weld direction, this is your weld bead metal. Over here, the metal to be deposited, this is my angle, right? Because you are doing preheating, here your rate of cooling gets reduced, right? So this is true, this is false, this is true, this is false. Let me know if you are not agree. We will have a final numerical. Okay, I'm moving to the last question of today's session. If you have attended the first session, there was a similar type of question on in terms of finding out the efficiency. So I have kept again same type of question as such. But yeah, uh, so hmm, let's quickly solve this question. In this numerical, it tells I have my heat transfer efficiency of a arc welding plate using welding current is known as 250 amp, voltage is known as 20 volt, and heat transfer efficiency is given as 90%, right? So what is my nominal power for this power source utilizing the heat transfer efficiency? So my Q nominal is equal to V into I into 0.9, right? So how much is this? This is 4,500 watt, not watt, sorry. This is in joule, right? Then I say that heat required to melt the material is 10 joule per mm cube. My cross-sectional area of the weld joint is 10 mm square. Travel speed is 5 mm per second. Time for welding is 5 seconds. So I need to determine the melting efficiency. So eta melting is equal to how much is my actual heat flux, that divided by the nominal one, right? So if my heat required to melt the material is 10 joule per mm cube, I need to multiply it with the volume of the melted material. That will give me the actual heat flux, and that divided by 4,500, right? So 10 into cross-sectional area is 10 mm square into 5 mm per second into time. Time is 5. How much is this coming? 2,500. So 2,500 by 4,500. So this is coming as something around 55.5% intermelting question.
I have a speak of.
Mhm.
Can you show me the question number three?
Question number 3.
Just show this.
Which one?
Question number three.
6.
No, no,
Stop
it's
it.
five. Question number five.
Question number 5. This one.
Just
Any confusion is there?
No, sir. Sir, in question number 5, and power is calculated.
I'm not getting you. What happened?
So in question number 4, in
In
last,
question number
the
4.
length and the power is calculated.
What happened? Length.
The, the how length is calculated.
Ah, so, okay. Uh, Till this you have understood how
Sir,
I have related power to the arc length.
sir.
So power will be coming as 1200 minus 800 L plus 2400